Hello, Ken. Hello, Miguel.
Hello, hello, hello. Uh, yeah. I was asking, why is Wednesday? Because the class should be Tuesday and Thursday, right? So, what are
Um,
today? Yeah.
could you? I didn't quite catch the first part of your question.
So,
Why?
our class is Tuesday and Thursday, right?
Yes.
Yeah.
The lecture
Today's
is
Wednesday,
Tuesday and Thursday. Yeah.
but today's Wednesday. So,
Right. Today is for. It's a section for the Wednesday lab. So this will be a repeat of what we did on Tuesday.
okay. And we will do it tomorrow.
Yes, and I'm going to do it again tomorrow
Okay. Okay.
at like 10 o'clock.
Okay. 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 So I see you tomorrow.
Alrighty. We'll see you tomorrow, sir.
Okay. See you.
Okay. Bye bye.
Bye bye.
Miguel, it's just you and me.
It is. Hi there.
Oh my God.
I guess no one's gonna show up, maybe.
I know. I was so slow getting out the stupid invitation. Ah. Oh my God.
But basically, today's gonna be the exact thing you posted on YouTube, right? The video.
Yep.
Oh, okay.
Exactly. So would do you, yeah, so
If no one shows up, I could just watch the video.
well, no. I want to make sure you get all your questions answered. I mean, it's a great opportunity
Yeah, that's true.
to get a complete hour of me uninterrupted. I mean, because you have to, not because you want to. Shoot. So, can you see my screen? You probably can't. There we go.
Yeah, I can. It's the Word document.
Yeah. Okay, good. I think I just um, it said sharing was paused, and I didn't pause it, but yeah, what I wanted to do was go over. Did you? You weren't in the Zoom lecture yesterday or the Zoom lab yesterday, were you?
No, I wasn't.
Okay, great, excellent. So, how are you doing in the class in general?
Pretty good. Good
Excellente,
so far.
excellente.
Yeah.
Yeah, did you get uh your lab report in the
Uh, the UV vis,
I know the ICP.
the
The
ICP. Yeah, I already got that. I already got.
excellent. Yeah, I remembered, but I didn't quite remember. So thank you.
And with
Good.
the UV vis,
Yeah.
by Friday, right?
Well,
Pretty much.
uh, uh, honestly, as soon as you can get it,
Okay.
turn it into me. Uh, if I get it by like the last week, then I won't count it late.
Oh, okay. Sounds good.
Yeah, but uh, it's just a huge. I don't know why I I don't have. It's because well, I kind of do know why. It's because in the past when we go into the short labs from the long labs,
Mhm.
there's about three different groups going at any time, and they all have different due dates, and there's three different labs. So it's really hard to set Canvas up. So I just set all the labs due at like the last week, but it that doesn't really serve you guys as students because then I mean as humans we're going to put it off, right?
Yeah, exactly. We're gonna push it to the last couple of days. But
Exactly.
I already got
Exactly.
the UV Vista, and I was just I looked up the on the lab manual. It's just a short report, cover page,
Right.
and a short
Right.
description. Okay.
Exactly. And so and one thing you can do is you can submit it with a question and say, Dr. T, can you look at this,
Hmm.
and make suggestions, and then I can, and you can turn it back in.
Oh, okay. That sounds
So
good.
that's it's sort of a um, I haven't really thought about it until this moment, but that's totally fine to do.
Okay, I'll probably do
So,
that.
hey, Alex.
Oh, we got another one.
Yeah, we do. Excellent. Hola, hola. How you doing, Alexis?
Oh, hi.
Hello, hello. Good morning. So
Good
you want
morning.
to talk about Raman?
Yep, sure.
Sounds good. Well, it's just you and Miguel and me.
Okay.
And can you see the screen?
Yeah, I can see it right now.
Excellent. I just got to answer a text here from my wife. All righty. So, are either of you familiar with Raman? Yay, nay? Let's see here.
Kind of, not really. I kind of
Okay. All righty.
Yeah, me neither. Not much.
Okay. So let's see here. I opened the chat thingy there so that we can kind of have back and forth that way if you guys like to. But so okay, well let me describe Raman to you guys both, and it's a simple technique in one sense is that all you need is a laser and a spectrometer basically. So the reason that you use a laser is you need a really bright, really monochromatic source. So you need like for example, you could use a helium neon laser and shine it into some hexane or I don't know, whatever, pick a molecule, right? And then, you know how sometimes when you shine a laser beam through the air, you can actually see the beam.
Yeah.
But then if it hits you, if it goes directly into your eye, it's like, oh my God, it's blinding. It's super bright. Yeah, that actually happened to me in high school. I can't believe it. In 1980, can you believe that? But so that's the reason that you can see the beam from the side is normally from dust in the air, right? Where the beam hits the dust and then it scatters all over the place. And then if you focus on that, on where the beam is, you can see basically the dust lit up, right? And so that's, that's like practically just normal reflection. But there is another phenomenon called Rayleigh scattering. And Rayleigh scattering is where literally the molecules in the empty space, they will scatter the light beam. They'll scatter the laser beam, and it's a fairly weak phenomenon. So like at visible wavelengths, maybe 1 in a million photons might be scattered by the atmosphere, let's say. But like if you go outside or you could have a view out your window, you look out into space, and instead of seeing the blackness of space and stars, you see the color blue. And that blue color comes from the scattering of sunlight off of the molecules in the atmosphere. There's also other contributions, but the majority of the blue color comes from the scattering of the visible light by the atmospheric molecules. And, you know, if you could collect a spectrum of that light, you'd see that it was, no, it's not purely monochromatic blue. It reflects the sun's spectrum, but it's shifted into the blue because the blue scatters about 4 times better than the red. So, so that increase in the scattering of the blue light is why the sky looks blue. Now, if instead of being irradiated with a broadband source, instead of the sun light scattering off of the atmospheric molecules, if you had a laser, let's say the entire Earth were bathed in a monochromatic beam of like a laser, right? You looked up into the sky, you would see that same laser wavelength. But then if you had a real sensitive spectrometer, you could look at it and also see that laser wavelength shifted a little bit. There'll be like copies of the laser scattering frequency, but at much lower intensity, right? So to follow along with the notes here, that weakly scattered light, it forms what are called side bands on the Rayleigh peak. And the side bands are called Raman scattering bands, after the Indian scientist C.V. Raman. And Raman discovered that the vibrational signatures of the scattering molecules are encoded in their scattered light. And if you analyze the scattered light, you see the vibrational spectrum literally copied in the scattered light. And this is called Raman scattering spectroscopy. You need a monochromatic light to do it, otherwise everything's all washed out. In other words, there's many, many wavelengths of sources, there'll be many, many wavelengths of scattering, and you can't sort anything out. But if you have this intense laser beam coming in, most of the light that scatters out is of the Rayleigh variety, where the scattered light frequency is equal to the incident light frequency. So you just see the same laser light frequency coming out. But for the Raman bands, there's an exchange of energy between the photons and the molecules in the atmosphere or whatever the sample is that you're looking at. And in that case, the scattered radiation frequency is not equal to the incident radiation frequency. And in the Rayleigh case, it is. And so in the Raman case, it's called inelastic scattering. In the Rayleigh case, it's called elastic scattering. So elastic meaning that all the energy is conserved. So it's like a rubber band where if you stretch it, and then it'll snap back and give the energy back. But inelastic is where it'll absorb some of that energy. Or, oddly, in the case of Raman, where you'll pick up a little bit of energy from the molecules. So in a Raman spectrometer, you've got a laser, and then it's normally focused to a point somewhere in a solution. And that point is imaged onto a spectrometer, and that's where the scattered radiation is picked up. And the sample is typically concentrated or solution or a neat liquid or a solid. It could also be a surface. But Raman is not normally used for dilute solutions, although there are enhancing media for it. We will not talk about them. So let's say, for example, that you've got a helium neon laser, 633 nanometers. The most of the scattered radiation will be at 633, or nanometers, which is equal to 15,803 wave numbers. Why do we convert to wave numbers? Well, as you'll see, we're equating the scattered wavelengths to the vibrational frequencies. Vibrational frequencies are normally given in wave numbers. So, when we look at the Rayleigh line here in a spectrum, you can see, I'm going to erase these. They're sort of answers. So, let's look at this hypothetical a Raman scattering spectrum, and this is with the x-axis of wavelength here in nanometers, and then we're looking at the scattered light power there. That's not too surprising. And what we see is a large peak. So this is a very large peak. Right? And then off on this is the red side. And this is the blue side. And by red and blue, I'm referring to the relative wavelengths. The relative wavelengths are longer. On the right and shorter on the left, right? So let me give these peaks letters. We'll call this A, B, C, D, and E. And why don't you guys chime in and tell me which of these peaks is the Rayleigh peak?
Would it be C?
Yes. Yes. So Miguel, did you catch that?
Yeah. C. Is that because it's like that's the one that's stretching the most out?
Exactly. It's exactly because it's the most intense peak.
Okay.
It's, that's what gives it away. Another thing, which is absent in my description here, is that this is using a 500 nanometer laser. And lambda is equal to lambda incident. Okay, so so of these, and this is equal to 500 nanometers. Of these 5 peaks, which are elastically scattered? Or which of these peaks represents photons or encodes photons that were scattered elastically?
Would it be on the right side, D and E?
Okay, so D and E. Alex, do you have an opinion here?
So if they don't gain any energy, would it be A and B? Or
Okay, so we got D, E, and A and B. All right, so so at 500, so E, the photon energy, right? What's the formula for photon energy? Either you guys know off the top?
I quite don't remember it.
Okay, it's 2 letters. First one's an H, and second one is
C.
it could be C, yeah. H, C divided by
Would it be frequency maybe?
so
Wavelength.
HC over lambda or H nu.
Okay.
HF or H nu is equal to F, right?
Yeah.
So that's because nu is equal to C over lambda, right? This is just the speed of light equation there, right? So the photon energy is equal to hc over lambda. It's also equal to h nu, right? And in this Raman spectrum, the Rayleigh peak is the peak where the observed frequency is equal to the incident. It's equal to the 500 nanometers. And that's equal to the laser. I should say lambda laser, right? Okay. So for elastic scattering, is energy lost or gained? Santiago, you're gone. Miguel.
Yeah.
Energy.
Elastically, it's conserved, right?
Right. Exactly. So for so we already identified the peak where the incident wavelength is equal to the laser wavelength, and that is peak C. So if the photon that's scattered has the same energy as a photon that's incident, then the wavelength of that scattered photon will have what relationship to the wavelength of incident? Let me repeat that. And there are 3 possibilities: greater than, less than, or equal to.
So would it be equal to or?
Miguel? So the answer is E is equal to hc over lambda. So h isn't changing, c isn't changing. So E is proportional to 1 over lambda, right?
Mm-hmm.
If E is the same, then lambda is the same.
Oh, okay.
Yep. So, and if E is the same, is that elastic or inelastic?
Elastic.
Yes, sir, bobber. Excellent. So we've got 4 guesses for which the elastic peak is: D, E, A, and B. Oops. Which is the correct answer?
Well, wouldn't C be also elastic though?
Well, I didn't say these were correct. You guys gave
Oh
me those
yeah. Well, Rayleigh peak is supposed to be elastic.
answers.
So I see.
Yes. Yay.
Okay.
Cool. All right. So the now Now we found an elastic peak. What are the inelastically scattered peaks?
Oh, that'd be the rest from A
The
B.
rest, exactly. A, B, D. Excellent. Cool. All right. So now the next question is which are Stokes and which are anti-Stokes? I did not define Stokes and anti-Stokes yet. A little history. Stokes, I think it's a name of a scientist who did spectroscopy back in the day, and the Stokes shift is always a red shift. So, and it means it's a process where a photon interacts with a molecule or something, and then the photon loses energy. So it's a way that photons can dissipate energy. So the Stokes peaks in this spectrum are what two peaks?
D and E.
D and E, exactamente. And the anti-Stokes are the ones where the photon gains energy. Those would be
On the blue side. So
exactly A and B. Now, why are the Stokes peaks more intense than the anti-Stokes peaks? All right.
yeah, that's a good question. Higher intensity. I don't know.
Yeah, so they're more intense because they're more intense. That's true. Now, what about? So now you have to. Now I'm asking you to think like a spectroscopist here. Say, well, what? Hypothetically, everything that's happening here is where there's just photons and molecules, right? And basically, we have photon h nu I. Wait, actually, let me just make myself some space here. Convenient. Make myself space by writing in the tiny, tiny, tiny font. Ah, no, come back. There we go. Okay. So we've got photon h nu I plus molecule, and then that makes h nu s, the scattered photon, plus a molecule, and the molecule can have plus or minus some energy. Right? So, so in order for this molecule, in order for M to make M minus delta E, this has to start out as M plus delta E, right? It has to have some energy to give away to a photon, right? So this is H nu I plus an excited state photon makes H nu scattered plus a ground state. Right? Now, there's also the possibility where we have H nu I plus molecule makes H nu scattered plus M plus delta E. Right? Now this is these two frequencies here are not the same. Let's call this 1 and this guy 2. Right? So we've got, instead of minus that, I'm going to just leave that as an M, right? In other words, if the photon finds an excited state molecule, it can scatter and leave a ground state molecule. So this is one type of Raman scattering. And this here is another type. So this is, say, the second type. Okay. So in the second type, we've got a ground state molecule makes an excited state. In the first case, we've got an excited state makes a ground state. So, so the rate of these interactions is going to be proportional to the light power, call it pi, right, times the concentration of the state with which it's interacting. Good enough so far?
Yeah.
Okay. Alexis?
Yeah.
Okay. So, which of these two processes, call it A and B, will have a higher rate?
Rate is equal to or is proportional to.
So pi is the same in both A and B. It's the same, right? So the difference is not in pi. The difference is in the state concentration. The brackets indicate concentration. And then state is either M star or M.
Would it be B in this? B?
Okay.
Or ground state too excited?
I appreciate your boldness. Why?
Not sure.
Okay.
Just a wild guess.
Well, it's not wild because it's a guess out of two things.
Or 50-50 chance.
Yeah, it's either A or B. Okay, it's a wild guess. I don't know, but which are more populous? Excited states like these guys, or ground states like these guys? Which, if you take, well, yeah, and so and these are vibrational states we're talking about. So if you take a collection of oscillators, right, and say, well, how many of these are in their ground state, and then how many are in their excited state, right? You just have like a bottle of these things. What state will be more populous? states. That is, in which state will there be more? Will there be more states? Will it be ground state or excited state?
Excited because it just keeps going up in energy states.
Mm-hmm. Alexis, what do you think?
Yeah, because if we're shining a laser on them, they'll be constantly excited, right?
Ah, excellent, excellent, excellent. Okay, these are okay. So this is a good point, right? Now, it is possible to produce more vibrationally excited states by irradiating them with a laser. That is possible, but um, in this case, the laser light intensity is low enough that only a tiny, 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 tiny fraction, like one in, it's like a millionth of a millionth of the molecules interact in this way. So it's 10 to the minus 1 and 10 to the 12th molecules interacts with the laser beam. So it's the question of how many are ground and how many are excited doesn't depend on this 1 part in 10 to the 12th. So I'm saying that you can't use the laser to explain why there are more excited states than ground states. And I didn't, and I have not really concurred yet with which state is more populous, A or B. We've got A and B. You guys guessed A, and I gave you a hard time. Therefore, the answer must be.
I said B, didn't I?
Okay, you said B. Okay,
So then
Alex. Alex, do you agree?
Yes, B.
All right, all right, all right. I heard A, damn it. And then I heard Alex say because we're irradiating it. Okay, so in fact, there are more ground states than there are excited states. There are many more ground states than excited states for the vibrational energies. You know, so that's actually it's true in most spectroscopy. It's true that there are many more ground states than excited states. For electronics spectroscopy, it's like don't even care about the ground states. There just are none, right? For vibrational, maybe there's 1 in 1,000 or 1 in 100, maybe if it's a very low energy vibration. But the number of ground states, or the number of states in a particular energy level E, is proportional to it's like KT times E to the minus delta E over KT. Sorry, it's the KT is not in the pre-exponential there. K T, it's just proportional to E to the minus delta E over KT. So whenever delta E is large, it's a negative exponential that gives the number of states at energy E divided by the number of states in energy 0, like the ground state. Does that make sense?
Yeah.
Okay. That's an important one to understand for doing for understanding spectroscopy. Here. I'm going to try to get a. Oh, I got 2 pages now. So let's review a couple thoughts here. First of all, this is called the Boltzmann distribution. Or the Boltzmann partition function, maybe. And that is that the number of states of energy E over N0 is equal to GE or G0 times E minus delta E over KT. In this case, G is the degeneracy. And then delta E is the energy. And then KT is the energy of the state here. And this is the thermal energy. Right? And then, so it follows that for most spectra, delta E is greater than KT. So N of E and 0 is typically less than 1 for comparable GE values. Oops, this is supposed to be E here. And then, let's see here. And then what we can say is that the rate of production of scattered photons, call that R, is equal to the light power, P, times N, you can call it N, right? And N is the number density or the concentration. Okay. So therefore, if Stokes, Raman, power, E sub S, is proportional to N0, and anti-Stokes Raman P anti-Stokes is proportional to N sub E, right? These are the intensities. Then the Which of these is going to be more intense, Stokes or the anti-Stokes? Oops.
Um,
Stokes or anti-Stokes? It'll be S or AS.
Stokes.
Okay. Great. Why? Correct. Why?
So it's light power. What's the NO? That's the
Oh,
number.
that. Oh, this is the number of ground states.
Oh, so ground station. The other one's excited.
Yeah. Yes, yes. These are ground states and excited states. And then there's NU, which is United States. I'm just kidding. That's stupid. Oops. Okay. So you said that the Stokes will be more intense, right? And that's correct. But why?
Um, is there
Actually, oops, sorry.
so
I made
is
a
it
mistake. Go ahead. Go ahead.
do they have a lower frequency than the anti-Stokes?
The okay, so there's photons and there's molecules, right? So there's uh, there's molecule plus incident photon makes molecule plus scattered photons. And I'm saying that this can either go down in energy or, okay, hold on. Basically, there's two processes. And so this either goes to M star or this M star. As this is S is just for scattered. And this is going to be Stokes. It's going to be anti-Stokes. Okay. So in this case, in the anti-Stokes case, the number of anti-Stokes that you produce depends on the number of excited state molecules that are in the solution at a given time. And remembering that the production is not important. It doesn't change the concentration really. Partly because they only last for literally 100 femtoseconds. Alexis,
Yes.
you're very quiet.
I'm just processing this.
Processing this barrage of bullshit coming your way, right?
Yeah.
Okay. So, which are more populous, M or M star?
M, right?
Right. Ground states are more populous. So this guy is, maybe 10 to the fourth to 1. Right? Therefore, are there more Stokes or more anti-Stokes photons produced? Are there more of these guys or more of these guys?
More Stokes, right?
Yes, there are. That is correct. Who said that, Miguel or Alexis?
Alexis.
Ah, he stole it from you, Miguel. I'm just kidding. So there are more Stokes photons produced because there's more ground states to make them from. Just like if you're out hunting ducks, and there's 10,000 green ducks and one red one, and you shoot randomly, you're going to shoot about 10,000 more green ones than red ones, So anyway, so that's really all I'm trying to say with this. It's an important point, and it's not necessarily an obvious one, right? Oops. Oh, there we go. So let's see here. So the difference between the Stokes and the anti-Stokes peaks has to do with population. Oh, shit. M versus M star. Because Stokes come from M, right? The ground states. And this is supposed to be a star. That's an even uglier star. There we go. Okay. So moving forward here, another blank page. This is more or less how this looks, right? That this is a scattering phenomenon, so it does not have a stationary intermediate state. It doesn't have a classic intermediate state. And this is why the Raman scattering is very weak. Is that basically these virtual state lifetimes are very short. And I don't know if that's exactly why they're weak, but we're breaking one of the cardinal rules of spectroscopy because we're saying that this scattering phenomenon happens even though there's no state, right? So normally spectroscopy happens when you go between states, right? Right? There's vibrations, right?
Mm.
And then there's fluorescence, right? When you go into the upper state and then you get the photon back, that's fluorescence. And then there's normal absorption, right? But what we're saying with Raman is that we're going into this virtual state. And virtual states are weird because they don't exist. So so that explains why they're weak, right? Now Um, uh, now let's talk about Stokes and anti-Stokes processes, right? In a Stokes process here, we've got a ground state photon comes up and then emits, right? Or it comes up, then it emits, or it comes up and then it emits, right? And this is sort of indicated here by this common line to which all the Stokes processes correspond, right? So if the length of this arrow, right, is proportional to EI, which is equal to H nu I, and I is for incident, right? Means the photon that is creating the process, the photon that's being scattered. And then there's a scattered photon here, and a scattered photon here, and a scattered photon here. Right? Now, explain to me which of these states is M and which of these states is M star.
What are the dash lines? We're looking at Stokes.
Absolutely.
The M would be the dash lines, and the
Okay, good. That's true. The dash lines are associated with an initial state M. So Stokes, remember, is M plus H nu makes M star plus H nu S. Right? So we've got state A, B, C, and D. And we've got M and M star. So M is which of these four states?
Wait, but M isn't a ground state, so
M is a ground state.
so then would it be A?
A is the answer. And M star is
B, C, and D.
Yep. B, C, and D. They're all different M stars. So this is how M plus H nu makes M star plus the Raman photon. There's the incident photon. There's the Raman photon. Yes. So now if M star makes M, we've got M star here. And they make M, that's anti-Stokes, right?
Yeah.
Excellent. So
Start to do
let's assign. So we've got 7 peaks here. 1, 2, 3, 4, 5, 6, 7. And we'll label these A, B, C, D, E, F, and G. Okay, 7 peaks. The red shifted peaks are Stokes or anti-Stokes.
Red is Stokes.
Excellent. Okay. Now, to which of these arrows, green, yellow, or red, should I assign peak E?
Peaky. Those are Stokes. E would be
It's going to be one of these 3.
Stokes.
Time's up. Just kidding.
Uh,
Okay.
and do the excited states, does it increase from B to D?
B to D. Like between like this B here.
No. I'm talking about the on the virtual state and the real
Oh,
state.
I'm so sorry. B to D. Right. Yes. So like the energy of these are 3 different states.
Mhm.
M star.
Yeah.
There's a B, like MB, MC, and MD are 3 different excited states. And MD is higher energy than MC, is higher energy than MB. It's higher energy than MA. Well, MA is a ground state.
Okay. So would E, the wavelength for E, be B?
It would be ding, 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 ding. Yay. It would be B, right?
Mhm.
Because B, the energy of this line here is most similar to the energy of this line, right? These are the Stokes processes. These are the Stokes processes on this side. The one closest in energy to the Rayleigh line is B. And this is really confusing having A, B, and C there. So let me instead of having them there, why don't I give these guys numbers 0, 1, 2, and 3, right? So peak E is a Stokes process, and this goes from state 0 to state 1, right? And F is a Stokes process, and G is a Stokes process. And what 2 states are involved with arrow F?
Um, the second person.
Uh-huh. The second meaning the second one of these guys, or?
Yeah, that'll be the yellow line, or
Uh-huh, exactly. This is green. And this is going to be yellow, right?
Mhm.
And what are this is the ground state and the excited state. And for the yellow one, the ground state will be what?
Would it also be 0?
Mm-hmm. The excited state will be
2.
2. And for peak G here, ground state will be
0, 2, 3.
exactly. And this is the red line, right? On the Stokes side. And on the anti-Stokes, we've got peak and state. Now, peak E involves what two states?
Peak E.
Mm-hmm. So,
Peak E wouldn't it be, that would be
No,
the
no.
Stoke side.
Sorry?
Isn't Peak E on the Stoke side?
Yes. Peak E is on the Stokes side, yes. So this is E right here.
Mm-hmm. So Peak E on the anti-Stoke, it should be from the first excited state to ground level, to ground state.
Oh, God. I'm so sorry. I'm so messed up here.
It
Right.
should be ABC, right?
So, yeah. So, oh gosh, yes. So sorry. These are A, B, and C, right? So this is actually,
No, I think you're right. Stokes is E, F, G. And
oh,
anti-Stoke.
Stokes is, right. Okay. E, F, and G. Thank you. And then the anti-Stokes are A, B, and C, right?
Yeah.
And, okay. Sorry.
Yeah, and then D is just the railing one.
Right. So peak A involves which two states? There's two states involved here.
Looking, let me see.
So peak A is way over here on the left, and this is anti-Stokes. This is blue, the blue side, and these are anti-Stokes. These are red. They're Stokes. So peak A.
Would that one be the first excited state to ground state?
Excellent. So the so we could say state 1 here to state 0, right?
Mm-hmm.
So 1, 0. And then peak B.
That would be the second excited state to ground state.
And the third one?
Third excited state to ground state.
Okay. All right. So now I've got to pick on you, right? Because of these 3 lines, the red, the yellow, and the green, which of them is most like the incident photon, the black incident photon? In which case are they the most closely matched in length?
Comparing the black ones on the anti-Stoke, or
Right. Yes.
that
The
would
black. Yeah. Go ahead. Sorry.
be the first black anti-Stoke line with the red arrow.
Right. These are the most similar. Right. And these are the most different.
Mm-hmm.
These last guys are the most different, right? So the most similar one involves what two states? It involves state 0, a virtual state, and state
The first excited state.
1. So 0 and 1, right? So because they're closest when you're involving 0 and 1, which of these three peaks is closest to the Rayleigh peak?
Peak C.
Right. So
Okay. Okay, I see that. Closest to the peak is going to result.
when I use arrows. So focus on peak C here. And tell me whether peak C is red, yellow, or green.
Peak C is red.
Okay. Peak C is red. That involves which two states?
It involves the first excited state and the ground state 0.
Exactly. So for peak C, we've got 1 to 0. Yeah?
Mhm. And then peak B is 2 to 0.
Yep.
And A 3 to 0.
Exactly right. Very good. Very good. Very good. Very good. Excelente. So that's where I'm going to stop today.
All right.
And what you're going to do is you're going to pick up the files from Canvas. So let me change the share that I'm going to use here. Canvas. There we go. And you're going to go to, can you see Canvas now?
Yeah.
Okay. You're going to go to Files. Go to Lab. And go to Raman data. And then this is one set of data. There's 4 spectra. There's acetone, ethyl acetate, toluene, and then a mixture of these 3 with no solvent. Right? And you can refer to the video that I posted about this. Actually, let me find that video for you. I was told you could just search my name here. Roger Ailes, Roger Stone, Roger Waters, Roger Federer. How about Roger Terrell? Sheesh. Roger Terrell. Rate my professor. Never look at that. It's just you, LinkedIn, Scholar, la la la. Oh, there's my ancestor. ResearchGate, Facebook. There's me as a dog. Let's see. There's me in 10 years. There's my CV. Oh, geez. Oh, cool. There's my 120S notes. There's my grave. Okay. So I think Roger Terrell been arrested. Oh my God. I've been arrested. Roger Terrell. Let's try YouTube. Oh, geez. Oh my God. Okay. Music, history, whatever. Pre-service. Oh, Roger Chicas. Roger Chicas. Terrell. This sucks, man. Oh, this is North Georgia. This does not work. Oh my God. So you have to follow the links that I gave you, I guess.
Yeah, I
let's see
followed
here.
you on
Yeah.
YouTube, so I did like it.
Okay, excellent. Great, great. So, Alexis, how are you doing?
Doing good so far.
Okay, cool. Do you have any questions for me? Questions? No?
I don't.
Alexis has no questions either, does he?
No question.
Okay, excellent. Alrighty, guys. So I'm going to shut up now then, and you can take a look at the video to see how to process the spectra and how I stumbled through this whole explanation with a larger group of people.
Okay.
And you could probably skip that whole thing because, anyway, or you could go through it, whatever. And then towards the end, I describe how to get to, oh, actually, no, what you can do is just go to the full Raman data lab workup, right? And it's this guy right here.
Mhm.
Excellent. Yeah, this is the one to look at. Okay, cool. Alrighty, guys.
All right.
So I
Thank you.
will, yeah, I'll be there tomorrow morning.
All right, then have a good one. Thank you.
Thank you, thank you, thank you. Bye-bye.
Bye.